on to our second type of induction proof, which is divisibility proofs. Okay, so we've done the formula for the sum of series. Now on to divisibility. All right, the steps are going to be the same. Okay, it's the same 3 steps we follow. The kind of little trick that we use to kind of prove it is different to the series ones. But I think there's a bit more variation in the series ones, that it tends to be the same way of solving them over and over again with these divisibility ones. So once you kind of get one of these, you'll be good for all of them. Whereas you might get some series and not others. There might be a slightly different way of kind of unlocking the proof. All right. These can be asked in 2 slightly different ways. You can be asked, prove by induction that 2 is a factor of 3 to the power of n minus 1 for all natural numbers. Or you can be asked, say, prove by induction that 9 to the power of n minus 5 to the power of n is divisible by 4 for all natural numbers. So they're asking you to do the same sort of thing. So that first one could be asked, prove that this is divisible by 2. This one could be asked, prove that 4 is a factor of this. Okay, so divisible by 2, 2 as a factor means the same thing. Divisible by 4, 4 as a factor means the same thing. And as I said, they can be asked either way. All right. So our 3 steps in solving are the same as any other induction questions. So let's do our first step, our P1. So we're trying to show P1 is true. So we're going to sub 1 in here, and hopefully we get something divisible by 2. All right. So let's just do P1. 3 to the power of 1 minus 1 is just 3 minus 1, which is 2. All right. So 2 is divisible by 2. Therefore, P1 is true. All right. Second step then is to assume PK is true. So I'm going to sub K in here for n. So just write down what our step is maybe. Assume PK is true. So that would be 3 to the power of k minus 1 is divisible by 2. Now, I think we can do a little bit better than that in terms of writing that mathematically. Okay, so rather than kind of that kind of clunky sentence, is divisible by 2, we are going to write that mathematically. So how could we write that? Well, 3 to the k minus 1 is equal to 2a, and just a is some whole number. Okay, a is an integer. So if you can factorize 2 out of something, it must be divisible by 2. Or if you can write something as 2 multiplied by something, it must be divisible by 2. So if this is divisible by 2, you must be able to write it as 2 times something. So like 2 is 2 times 1. If this was 4, that'd be 2 times 2. If this was 16, it'd be 2 times 8. If this was 100, it would be 2 times 50. Okay, so that's our kind of mathematical way of writing something is divisible by 2. Okay, while we're only proving this for natural numbers, the a here can be any whole number, so it can be negative as well. Don't worry too much about that. Let's say if that minus there was a bit bigger, this could end up being negative. But look, that's there for completeness. I think you'd get away without writing that. But that's how we write something is divisible by 2, and you'll do that step every single time. If the question was is divisible by 3, you'd have equal to 3a. If the question was is divisible by 11, you'd have equal to 11a. All right. There's another line I'm going to put in here. I'm just going to leave a gap for now, and go on to step 3, which is to prove p k plus 1. Okay, so that just means sub k plus 1 in there for n. All right, so 3 to the k plus 1 minus 1 is divisible by 2. All right, you can write kind of equals 2b, nearly equal, introduce another kind of more mathematical way of writing that, but we'll kind of get away with writing this like this and then just kind of working away on this until we can factorize 2 out. Okay, so what are we going to do here? 3 to the power of k plus 1. All right, what I want to do here is get a 3 to the power of k out of that, and then do some subbing in from my assumption step into my proving step, like I did with the series ones. So I need to break this up in some way to just get 3k on its own. Okay, and what I'm going to use is a rule of indices that you've been using all the way since first year. Not as familiar with seeing it done this way around, but let's say if you had 3 to the power of 2 multiplied by 3 to the power of 4, what can you do? Because they're the same base, you can add those powers. So that will be equal to 3 to the power of 2 plus 4, which is 3 to the power of 6. Okay, so that's the more typical way we do it. What we're going to do here is go back that way. So we have 3 to the power of k plus 1. So we're going to rewrite that as 3 to the power of k multiplied by 3 to the power of 1. All right, so I've got 3 to the power of 1 multiplied by 3 to the power of k. All right, so I could rewrite that as 3 to the power of k plus 1 minus 1. You can stop writing the is divisible by 2 for now. We'll return to that at the end. So you've got your 3 to the k here. You've got your 3 to the k here, but it isn't kind of on its own. It's not isolated. So you want to isolate that 3 to the power of k, get it on its own before you do your subbing in. So 3 to the k is equal to 2a. Bring the minus 1 over. It becomes plus 1. So now you have 3 to the k on its own. So you can sub this in for 3 to the k in this question. All right. I'll carry it on up here. So 3 to the power of 1 is just 3 on. Instead of 3 to the power of k, I'm going to write 2a plus 1. And then I've got minus 1. 3 times 2a is 6a. 3 times 1 is 3. And I've got my minus 1 at the end, which is equal to 6a. 3 minus 1 is 2. 6 and 2, you can factorize 2 out. All right, so at this step here, you need to be able to factorize 2 out. Okay, if you're not, if you got 3 there, or 5 there, or 7 there, or something that you couldn't factorize a 2 out of, something's gone wrong. All right, so factorize the 2 out. 6a divided by 2 is 3a. 2 divided by 2 is 1, and that is divisible by 2. Okay, as long as you can factorize 2 out of something, rewrite it as 2 multiplied by something, that means it's divisible by 2. Okay, which is equal to that, which is divisible by 2. Therefore, you can write therefore 2 is a factor of that for all n is an element of n, or you can kind of return to our kind of p notation in there and say therefore Pn is true for all natural numbers. Okay, or as I said, instead of Pn you could write 2 is a factor of that for all natural numbers. All right, but that's our first example done. I'll do the other one in this video as well. So prove by induction that 9 to the n minus 5 to the n is divisible by 4 for all natural numbers. Okay, so asked slightly differently, asked in terms of divisibility rather than in terms of a factor, but it's asking you to do the exact same thing. All right, so same 3 steps will always follow for these ones. So step 1 is to do p to the 1, so sub 1 in for n. 9 to the 1 minus 5 to the 1 is 9 minus 5, which is 4. Okay, 4 is divisible by 4. Therefore, P1 is true. So we're showing P1 is true. Second step, assume PK is true. So we're going to sub K in here. So 9 to the K minus 5 to the K is divisible by 4, or you can kind of skip straight to your equals 4a. A is an element. That's it. So A is a whole number there. Grand. All right. So we know we're going to need our step here. Again, I'll just leave it and kind of start into my step 3 first. So what do I do here? I do 9 to the K plus 1. Sorry, so write out what the step is. Prove P to the K plus 1 is true, or just prove P to the K plus 1. So 9 to the K plus 1 minus 5 to the K plus 1 is divisible by 4. Okay. So what's different with this one is you've kind of got two choices here almost in terms of what you're able to isolate up here. So you could write 9 to the K equals something, or you could write 5 to the K is equal to something and do a bit more moving around. Either one will work. Okay. What I'm going to do is I'm going to isolate the 9 to the K up here. So 9 to the K is equal to 4a plus 5 to the K, bringing that around. Okay, so this is what I'm going to look to sub in here. Okay, regardless of which one you isolate up here, you still need to break both of these up. Okay, so you need to rewrite this as 9 to the power of 1 multiplied by 9 to the power of K, and you need to write this one as 5 to the power of 1 times 5 to the power of K. Alright, so it doesn't matter if you're going to write this as 9 to the K equals something or 5 to the K is equal to something, you still need to break both of them up. Alright, it's the 9 to the K I've isolated, so it's that I'm going to plug in. So I've got 9 times, instead of 9 to the K, this, so 4a plus 5 to the K, and then minus 5 to the power of 1 is just 5 times 5 to the K. Moving up here to finish it off then. So multiply your 9 in. So 9 times 4a is 36a. Just be careful here. 9 times 5k is not 45 to the k. Okay, this is raised to some power. So you would need to evaluate that first before multiplying by 9. Okay, so you can't, that is not 45 to the power of k. So all you're going to write for that one is plus 9 times 5 to the k. And then you've got your minus 5 times 5 to the k. And same thing, okay? You can't multiply that in. 5 times 5 to the k is not 25 to the k. All right? But what you'll notice is you've got 9 times 5 to the k minus 5 times 5 to the k. So you've got 9 of something, take away 5 of something. If you have 9 of something and you take away 5 of something, you have 4 of that thing. So this is equal to 36a plus 9 minus 5 is 4 times 5 to the k. So like the 5 to the k there is just like x or any other kind of variable you'd like to add and subtract. So you've got like terms there if you like. So 36a plus 4 times 5 to the k. I'm trying to prove this thing is divisible by 4. I do that by factorising 4 out. Can I factorise 4 out of both of these? Yes, I can. If I factorise 4 out of these, 36a divided by 4 is just 9a. 4 times 5 to the k divided by 4 is just 5 to the k. Okay, you've factorised by 4. It's 4 times something, so that must be divisible by 4. So, which is divisible by 4. Therefore, 9 to the n minus 5 to the n is divisible by 4 for all natural numbers, or if you like, p to the n is true for all natural numbers. Okay, as I said, that one equally would have worked if I had have rearranged this differently and got 5 to the k equals 9 to the k minus 4a and subbed that in there. It still would have worked out that I would have been able to factorize 4 out, so that's fine. It's up to you. You'll also often get these with +1 or to some number at the end as well, so kind of a mix of these. Okay, but look, it's you will solve it the same way as you solve this one. You just have some constant like +1 or something at the end here. You will solve it in the exact same way.